All right, one of my students asked me for a video on modeling and optimization. I sort of assume that the problem is the modeling, writing the equations, but I'll give you both just in case. If you're going to be successful, you need to have a diagram, or at least according to me, so that way you understand the situation and can create the correct variables. That's another problem. A lot of people don't identify the correct variables or what they're trying to find, which means they struggle to get where they're going. Once you have the correct variables, and as few as possible, you can make an equation. That's the thing you're going to find the maximum or a minimum of. And then you're going to justify, which is usually something like the first derivative of f changes from negative to positive, so local minimum, all that stuff. I think this first one's pretty easy. Two numbers whose sum is 8 and whose product is as large as possible. How would you draw that diagram? I would just draw two boxes because I don't even know that the numbers are single digits. So I'm going to say x is the first number. I can say y is the first number, but that's going to be a little bit of work. I'll just have to rearrange because, let's see if I can explain this. Right now, I want the product of the two numbers, so let's call that function f. I want the product of those two numbers to be as large as possible, but x times y is not the type of thing you're going to be able to take the first derivative of and find a local maximum or a local minimum. So instead of the second number being y, well, the two numbers add to 8. So let's call that second number y temporarily, which means x plus y equals 8, and y is 8 minus x. So if we can, we'd rather have everything in one variable like we do now, because now we can say, maybe I'll use p for product. Our product function with an input of x is the first number, x, times the second number, 8 minus x. That's the type of function, let's rewrite, negative x squared plus 8x, that definitely has a maximum. You should be thinking an inverted parabola definitely has a maximum. Okay. Before we find the derivative of our product function, do we have any domain restrictions? It says two numbers. Can we use negative numbers? Yes. Can we use positive numbers? Yes. So x, well, I guess that's not really anything, but I'm trying to write. So x can really be any number. Okay, so let's see. P prime of x, that's easy, negative 2x plus 8. And that's a polynomial, so we only have to worry about p prime equal to 0. Which means, of course, x is equal to 4. Now, a lot of people make a mistake of stopping at that x equals 4, but you need to justify. This is AP Calculus. So let's change our color so we get to the justification part. In order to justify, we're going to need a sign chart. 4 on this sign chart. These are x values, and this gives us the sign of p prime. So let's choose a number less than 4. We're probably all choosing 0, which makes p prime equal to 8, and p prime is positive, which means p increases for values less than 4. Choose a number greater than 4, like a million. P prime is negative, p decreases for values greater than 4, which is what we were thinking anyways. That matches the inverted parabola we were already thinking. Okay, so now we need to justify. So let's see. P of x is continuous. That's important because a function can't have a local maximum if that function is not continuous at that place. And we can just put period, p is continuous everywhere. P prime changes from positive to negative. At x equals 4. So p of x has a local maximum when x equals 4. Okay, So that's the justification, but that isn't really an answer. It told us to find two numbers that have this sum of 8. So I need to go back and say, let's see, and the product is maximized. Okay, the two numbers are 4, and they'll be able to figure out that's the 4 I referred to, and what's my second number? 8 minus 4, which is also 4. Okay, there's our first example. Let's go back and say what we did. We tried to draw a diagram. We labeled everything. We got down to one variable instead of x and y. We made that just all in terms of x. We made our equation, which was that product. We found our maximum. We justified, and then we actually wrote the answer. So for the rest of these, that last part's all going to be the same. The justification and answer, I'm going to work more on the modeling. This problem asked me to find the largest area, so I'm going to be writing an area equation, and that's what I'm going to take the first derivative of and look for where that first derivative changes from positive to negative, looking that we have a largest area. Okay. So either way, we're talking about rectangles. We know what rectangles look like. And maybe we'll use length and width for now. We don't want to use two variables if possible. So let's see. I don't think we also need to label L or W. Those are pretty standard for rectangles. And can you figure out what the length is in terms of the width? It's actually 6 minus the width. Or you could say the width is 6 minus length. How come? Well, twice length plus twice width is always perimeter, and this perimeter is 12, so length plus width is 6. And you can see from there, just subtract either L or W from both sides of that equation. So again, we're looking for largest area, so how do you find the area of a rectangle? Well, that's length times width, so W times 6 minus W. And what do we get? Negative W squared plus 6W. Is that the type of equation that's going to have largest output? Sure. That's a parabola opening downwards. And unlike the last problem, this does have a domain restriction. Let's see. Length and width have to be positive. So let's see. W, our input, is definitely greater than 0. But if you'll notice over here, length has to be 6 minus W. W also has to be less than 6. I'm hoping from there everything's pretty easy. A prime is negative 2W plus 6. Set A prime equal to 0. Make a sign chart. And let's see, A prime is going to change from positive to negative at 3. I'm choosing like 1 into A prime, and then 5 into A prime. You always want to use extreme values if possible. And then you're just going to say, well, A has a local maximum at 3 because A prime changes from positive to negative at 3, so stuff about areas and rectangles. I'm trying to go quickly because I know you're not going to watch everything. So I want to break down the questions and write the equations. Ooh, lot to do here. A farmer has a fen. He wants to make a rectangular pasture adjacent to a river. Here's the river. Ooh, maybe we should make the river blue. Now, this is AP Calculus, so that river is straight, even though we're not told that. So here's my fencing. And this is 180,000 square meters. Okay. What dimensions are going to require the least amount of fencing if no fence is needed along the river? So, still rectangles and areas. We're going to be a little more specific here. So I'm going to call, I guess I'll call this width, and W is going to be the length of fence, or width of fence, parallel to the river. Okay. You can't just say length of the fence and the width of the fence, because they act very differently. This isn't just a big rectangle in the middle of the field. So, can you figure out what the other side length is going to be? Well, it means the length of fence perpendicular to the river. And what's that going to be? Well, length times width gives you this area we have to provide. So this is 180,000 divided by width. If you needed to write that out, we could just call that side L for a minute. L times W is 180,000. And if you want L, you'll have to divide by W. Okay. So, again, we're looking for least amount of fencing, so I guess I'm going to call this fence as an input of W. Well, how much fencing do I need? I definitely need one W. I don't need two Ws. No fence is needed along the river. Okay. And I need two versions of length, but I don't want to use length. I'll use 180,000 over W, what length is equal to. Okay, what about domain here? Well, W is a dimension in the real world, or a length, so we need to have a positive width. And, well, it feels like W should have an upper bound, but turns out it doesn't. Could the width be, as an answer, maybe everybody likes a million? Could the width be a million? Sure. And then the length would be 180,000 divided by a million. I don't exactly know what that is, but that's pretty easy. That's going to be, I don't know, less than 1. That's going to be a pretty weird corral for, what are these? Herd. Maybe they're sheep, maybe they're cows, but that's definitely a real number, 180,000 divided by a million. Although we just know that's not going to hold sheep or goats or something like that very well. Okay. So from there, the rest is pretty easy. Take the first derivative of FW, look for where that first derivative changes. What do we want? Least amount from negative to positive, and we should be good to go. Ooh, posts in the ground. Two posts, one 12 feet high and the other 28 feet high, stand 30 feet apart. Okay, so there's my ground. Here's a post 12 feet high. Here's another one 28 feet high, and they are 30 feet apart. Okay. They are to be stayed by two wires attached to a single stake running from ground level to the top of each post. Okay, I know what stakes are. If you've ever seen wires attached to telephone poles into the ground so they don't sway, that's what we're talking about. Where should the stake be placed to use the least wire? So those two green wires I just drew, we want the minimum length of those. All right, so how do we set that up? Well, at least I know my equation is going to be length as a function of, I have no idea what. And that length is going to be the wire to the 12-foot pole plus the length of wire to the 28-foot pole. Okay, so that's my plan. So what's my unknown? My unknown is how far I need to place that stake. It doesn't give me anything, so I guess I will just call, I'll call this length x. What's x? X is the distance from the 12-foot pole to place the stake, or drive the stake in the ground. Now, it doesn't tell me, but if I want the least amount of wire, the two poles and the stake are all in a straight line. Okay, so do you see two right triangles? I hope you do. One right triangle over here has a side length 12, a side length x, and this side is 12 squared plus x squared inside its square root. That's actually the length of the wire to the 12-foot pole. Ooh, ugly, ugly one. Okay, well, the other triangle is a little bit uglier, but we can still deal with it. So this side length is 28, and the horizontal leg is definitely not x. The whole length is 30, and we already used up x. So what is the length of the wire along that diagonal? 28 squared plus 30 minus x squared. Okay. So that's the equation I'm going to take the derivative of. I'll probably do a little simplifying first to make my life easier, but let's think about domain. Now, can x be negative? Yeah, but we know that's not going to be part of the answer. And I don't really think I can drive the stake in the exact same spot as the pole, so x definitely has to be greater than 0. And by the same logic, we can't drive the stake into the other pole, the 28-foot pole, so x should be between 0 and 30. Are you reading, or should I read this to you? I'm going to take a sip of water. All right. 3 equal rectangles. I don't think that matters which direction. It's just going to be easier for me to draw this way. Now, I'm thinking ahead. I could definitely call this whole length x, but that would make this x over 3, which isn't horrible. But I can make my life easier calling those side lengths x and that one y. Okay. So we're going to maximize the area. So I already know what I'm going to write. I'm going to write my area is 3x times y, but I want to get that down to one variable. So how do I do that? That's this 400 feet of fencing material. So 400 is equal to all the fences added together. Can you count those up? How many y lengths are there? 3 of them. Oh, that's a lie. Good thing I counted. I would have looked silly. 4 of them. And how many x's are there? I think it's 6, but let's draw those in and make sure I'm not crazy. 2, 3, 4, 5, 6. Okay. So you have your choice. Do you want to solve for x or solve for y? Neither one's great. Neither one's horrible. So I guess, I don't know. For some reason, I like x's better. So 400 minus 6x divided by 4 is equal to y. And the area is going to be 3x times that. I'm sure from there you can distribute and find the derivative. Let's go back and say what x and y are. X is the fence length how do I say that? Of each interior corral. Y is the overall corral. I don't like that. How can I say I'm going to go back and change that. So y is going to be the length of the interior fences And x is going to be the length. Maybe I should use width. That feels like perpendicular. Okay. I think that's what I'm going to call x. The width of each interior corral, okay, not the whole corral, perpendicular to the interior fences. I think that's good. I said each, which I think implies 3 x's, not just 1. I'm hoping from there you can find a prime, look for the local maximum of a based on a prime changing from positive to negative. If you're still watching, I'm assuming you're okay with reading yourself. All right, this should be interesting. So here's our cylinder. This has a volume of 1,000 centimeters cubed. We're going to minimize the manufacturing cost. So this is going to be cost thing, which is why I'm given how to do all of this stuff. Okay, so the volume is pi times the radius squared times the height. So I'm given 1,000 is pi radius squared height. And that seems easier to solve for h, which is what I'm going to do. So h, the height, is going to be 1,000 over pi r squared. Okay. Let's see. The top and bottom are expensive to manufacture. They cost ½ cent per square centimeter. So let's see. Let's think about this. So the cost is going to be 1/2 cent. Ooh, not 1/2. 0.05. 5 cents for the area of the top and bottom. And then 3 cents multiplied by, that's actually called the lateral area. Or, I don't know, the area that's going to be covered by the soup can label, something like that. So, what's the area of the top? The area of the top is just a circle, so your cost is going to be 5 cents times pi r squared. And then the top and bottom are identical. We'll multiply by 2. What's the lateral area? That's actually a little harder to figure out. How do I explain that? Well, imagine you have some scissors and you cut right here. You would end up well, that was actually a pretty good drawing, with something like this. And if you unrolled it, you'd actually have a rectangle. Now, the height of that rectangle is going to be the height of the cylinder, which we already figured out is 1,000 over pi r squared. The question is, what's this? The length of the rectangle? Well, the length of the rectangle is actually the circumference of this top. And so the circumference of a circle is 2 pi times the radius. So this is going to be 2 pi times the radius times 1,000 over pi r squared. All right, I'm going to erase this diagram down at the bottom so I can clean some stuff up. So the cost as a function of the radius is going to be 0.1 pi r squared plus, so pi is going to divide, 1 radius will divide, and 0.03, that's going to be 3 over 2 r. Hopefully you know the radius is greater than 0. I should probably write that the other direction. And is there an upper bound on what the radius can be? Of course there's not. Because our only constraint is that we get the correct volume. Look back here. Can we have a radius of 1,000,000? Yes, that's just going to be a very short can. That's allowed, although we know it's not going to be the answer. So I'm going to assume from there, you can find C prime. I'm going to stop there. I hope that's enough.